Hello dear students, today we are going to discuss about one of the basic mathematical symbol that we use in this electrodynamics, that is called Levi Civita symbol, right? So you might have come across this symbol in some of the lectures that we have that I basically gave in last 1 month, right? So first, this is basically helps us to determine the cross product between the two vectors. Like if we have this A cross B, we have two vectors, right? If you want to calculate this I component, so you can write it in terms of this epsilon, which is called Levi Civita symbol, epsilon ijk, aj, bk, and this is basically, so you are calculating the I component of this, right? So this you can find it with the help of this this expression by inserting this Levi Civita symbol and with the following properties. Thank you. That's epsilon ijk, epsilon lmn. So we can prove that it is equal to the determinant of that delta lm. So you can see that. So it is, you can have all the possible these indices in this determinant. So we have to prove this. Our left hand side equal to right hand side, right? So before that, we will prove this because we know the basic property of this Levi Civita symbol as we have already discussed it, right? Now, so there is one more property that if we assume that if any two ijk are same, if we assume that if any two ijk are same, okay. So if we consider any two ijk are same, like if we have that epsilon iik or epsilon jjk or epsilon ikk, right? Or you can say that, or for this, for second epsilon we have that element. So if any of these two indices are same, right? So in that case, our this epsilon will be 0 because it is clear from this basic property of this Levi Civita symbol that if we have, there's a repetition of these indices, like then in that case, like we have that epsilon iik, right? That is equal to 0, or that's equal to epsilon jj, right? And similarly, you can also write for this if we have these indices element, because we have two epsilons. I am taking the product of two epsilons, and I need to prove that the product of these epsilons, that's equal to the determinant of this, right? So what is this? These are basically that canonical deltas, right? So canonical deltas, you have that basic property that delta ik that's equal to 1 if pi equal to k, right? And it is equal to 0 if pi is not equal to. So we are basically writing these Levi Civita symbols in terms of these canonical deltas, right? So first, let us prove that our right hand side equal to left hand side, right? So first, as I mentioned here, that if there is a repetition of these indices, like if we have this repetition of epsilon iik or epsilon jjk or epsilon kk pi, right? So or similarly for other this elements, so this will be equal to 0. So in that case, our left hand side will be equal to 0, right? Because our LHS will be 0 in that case. So let's have a look on the right hand side. So on the right hand side, if there is repetition, so you check that if there is repetition, if I is equal to it is equal to delta 1 1, it is delta 2 2 delta 2 3. Similarly, if you write for this one, if any of the two rows or two columns are equal, right? Or you can write for so if any of the two rows or two columns are equal, so in that case our right hand side will be equal to 0, because this is the basic property of the determinant, right? So like if we have that 1 1 2 1 1 1 3 3 3 and 1 5 7, right? If we have a determinant like this, right? So in that case we have two rows are equal, right? So in that case, the value of this determinant will be equal to 0, right? So this is what I told you, our right hand side will be equal to 0 in that case, right? So this is first property. So where we have seen that our right hand side will be equal to left hand side if there is a repetition of the indices, if any other two indices are equal. For this epsilon, similarly you can also write have a look on the determinant on our right hand side, so that's also equal to 0. So this is first case while our right hand side equal to left hand side. Second property is that if we consider that if I equal to L here, Second property, if we have that I equal to M, J equal to M, or K equal to M, right? So for this, so we can have, so when I equal to L, so following the basic property of this canonical delta, we have that if this I equal to K or I equal to L, I equal to M, J equal to M or K is equal to N. So in that case, we have only those diagonal elements will be 1. So because when I is equal to, when I equal to L, so this will be equal to 1. This will be equal to 1, this will be equal to 1, right? So our right hand side will be, in that case, our right hand side will be equal to, so we can have this 1, 1 and 1 on the diagonal elements. What about these? Because in that case, in this case, our I is not equal to M, because I is equal to L already, right? So this will be 0, this will be 0, this will be 0, this will be 0. So the value of this determinant will be equal to, right? Okay. And similarly, if you calculate now, so if you have a look on the right hand side, so what will be our right hand side then? Because our right hand side is left hand side, sorry. So our left hand side is basically, that is epsilon I j k, epsilon L M and N. So in that case, we are saying that when I equal to L, J equal to M and K equal to N. So in that case, because this will be equal to 1, right? Because you have that epsilon ijk, epsilon ijk. So this is epsilon ijk, epsilon ij. So this will be equal to 1, right? So in second case also, our right hand side is equal to left hand, right? So following these, if we calculate for the different conditions, like if there is repetition of indices, like if it is ij epsilon iik, so this is equal to 0, or if you consider that if our I equal to L, J equal to M, K equal to, in both the cases our right hand side equal to left hand side. So that means if we have, so it is in general we can write for any this, if we have the product of these epsilons like ijk and epsilon ln. So you can write it. So how you can remember it? So this is very easy to remember, because so the first indices of this one. So write that this epsilon in terms of delta. So we have all deltas here. Delta. Right? Then this, because it has indices and ijk, right? First row wise. So I here, here I, here I. Then for second, put a J, J, then K, K. So this is coming from this first, this epsilon ijk. And similarly, another this second this epsilon, it has these indices ln. So write first for this L, then M, then N, L, N. Right? So in that way you can remember it. If you have the product of these two epsilons, so you can write it in terms of the determinant. And because we need this to prove that if we have this product of these indices, we can write it in terms of this conical product of two these epsilons in terms of this conical delta. But now instead of that, if I write now this epsilon ijk, epsilon kln. So instead, earlier I basically used that epsilon ln, right? So that means, so you remember, so how to write these in terms of these deltas. So put that first that delta I, then j, and then put the second this indices on the each these conical delta, right? Now if you want to expand this, so let's expand this determinant. So its value will be equal to, so first one will be delta ik, right? So inside will be delta j, delta km minus. So this is the first when you expand this with respect from this one, right? And similarly, second one will be, that will be minus delta IL, delta JK, So this is when you expand this one, okay, because it's minus sign here. And now the third one will be that will be plus delta n delta dk. Right? Okay. So this is clear because so you remember that I told you in one of my lecture that it is basically this is a dummy indices because this is there is a repetition of this k here because it's ijk here it's km, right? So this is the dummy indices. You can take summation over that k, right? Now I basically expand all these with respect to this first, second, and third. Now if you have a look on the first one, right? So first one tells us that if you put that I equal to k, right? So I equal to k, so but j is equal to already equal to m. Then j equal to l, so this will be equal to 1, but k is also equal to m. So that means that k is equal to I, right? So instead of this, I can write this as, so this will be delta j delta I, right? Because it is coming from this one because it is there is a repetition of this k, right? So when you put I equal to k, right? But k is already equal to m. When k equal to m, so this will be instead of k you put here I because I equal to k. So instead of this k you put here I. So it will be delta m. Now instead of these three canonical deltas, you can write it in terms of two deltas, right? So by putting I equal to k, but k is also equal to m. So that means it will be delta im. And second is this is delta j, right? So this is first one and I expand this. So using the property of that canonical delta. And now let's have a look on the second term. So second term tells us that so this is so you can see here. So you can write that when I equal to k, right? Right? But k is also equal to m, l, right? And j equal to m, right? So let me write it. I'll explain this. So how you can remember this? So this will be minus delta j delta I, right? So that means when you put I equal to k, so this will be equal to 1. So this will be when you put I equal to k, so that means rest of k you put here I, right? Because here I equal to k because this delta is product of to these two deltas. So when you put I equal to k, so this will be equal to 1, but here I equal to k, so this will be delta I. So this is what I wrote here delta I, and this is as it is that is delta j. So this is second term, right? So instead of these three canonical deltas, you can contract it and you can write it in terms of two deltas, right? Now let's have a look on the second term. So second term is basically you can write that. So when I equal to l, right? When I equal to l, but l is further equal to m, k. So you can instead of this you can write that it will be minus delta j k, but k is equal to l. So you can write that it will be delta ik. So delta L, sorry, so this is I equal to L J, right? So you can check because here you are writing this delta as it is. Okay, so this is what I wrote here delta L, same as this one, right? Now here I am basically making change. Here I am saying that if our J is equal to K, but K is further equal to L, right? So that means our J equal to L because J equal to K, but K is further equal to L. So that means then J is equal to L. So instead of this, I will write delta Ij, and this when J equal to K, but K is also equal to this one. So you can write delta J into L, delta J L. Okay. Now let's have a look on the second term. So this will be plus now. So this will be plus term. Now because you just check this one. So this is delta KK. So delta KK is basically corresponding to those diagonal elements of this. If you write this delta in terms of that the determinant, so that will be some 100, because this delta k is something you can write it as this way. So this will be that delta k will be like, we have this, it will be that 1 0 0 0 1 0 0 0. It is like that, because you have that only the diagonal elements will be non-zero. So it will be equal to 1, so rest will be 0, because it is kk. But you need to, you have to take the summation of this. So it will be then 1 plus 1 plus 1. Calculated space. So this will be 3 times. Okay. So instead of this delta kk, you write 3 here. Okay. So instead of the second term from this one, so you can write that. So that will be equal to 3 times, because 3 comes from here delta kk. So this will be 3 delta ion, right, and delta jm, right. Okay. Sorry, ion delta jm. Okay. Now similarly, let's have a look on the last term here, right. So last term, similarly, it gives me, so you can check. So this gives me delta ion. So this is as it is. Now I'm making only change here, because here it is basically repetition is here, right? It is j k k. So that means when j equal to k, this is equal to 1, then k is further equal to l, right? So instead of this, so that means j will be equal to l in that case, right? So instead of this, I will write this is equal to j, right? Now last one will be the minus, because it is minus plus, it will be minus. Now again there is delta kk in this one also. So this will be again thrice, because it corresponds to those diagonal elements. You need to sum up, because as per this Einstein's summation convention, you need to sum over that our domain indices. So this will be equal to 3, right? Because it has only that diagonal elements will be 1 1 1, and the rest will be off diagonal elements will be 0. So you can have, then instead of this delta k, it will be 3, right? So I will get here. So this will be minus 3 times delta I, okay, delta j. Okay. So this is clear now, because here it is delta ion and delta j. Okay. And that the product of two these epsilons. So this you can write it this way, right? Now you just check. So there is, you can combine some of the terms here. So first this is, you can combine this term, the underlying term, that is delta j and delta ion. That is here delta j and delta ion. You can combine this term, and delta j delta JL delta ion, and one more term is, that is this term delta JM delta ion, huh? Delta JL, sorry, this was delta JL, I basically did a mistake. So these, so you can combine these two terms, one, first and third, right? So first and last two terms, right? So when you combine, so this is plus twice, this is minus. So instead of this, you will get minus here. So first term will be, instead of these three terms, underlying terms. So we will get here, that is minus delta IM delta GM, right? Now if you check these terms and that term. So this is basically JMI, 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 right? Now this is minus, this is plus. So you get here plus delta IL delta G, right? So that we can write now, because I need to use this property in my coming lectures. So we will discuss that in our course, that if we have this epsilon ijk epsilon klm, so this I can write as delta il delta j minus delta in delta g, right? So in general, or you can write that this product will be equal to that determinant of that. You can that you wrote in terms of these conical deltas, or you can write in terms of these delta difference of this. So that means So you need to remember only. So when there's a repetition, of one of the indices, that dummy indices that I wrote here, there's a repetition of this k indices, right? So take the product of first with the this fifth one and second with the sixth one. So you can remember that way. This I with L, J with M. Then take cross of that because it is you don't find that k here. So just check. So when you evaluate that, so you don't find because k is our domain indices. So you are taking summation over k here, right? So that's why you can write this as. So that means you take the possible combination of this with this. Sorry, this with this, right? So I with L, J with M, then I with M, J with M, right? So this way you can remember that product of these two.